Hi and welcome to the 6th year higher level maths revision video where we're going to review revision worksheet 8, which is a section B focus on trigonometry. So as a section B question, this is quite wordy and there's a lot of information here, so it's important that we take our time and read this properly. So the London Eye is the most popular paid tourist attraction in Britain with over 3.5 million visitors annually. The design principle behind the London Eye is very similar to that of a Ferris wheel, but it's actually an observation wheel. The wheel's 32 passenger capsules are attached to the external circumference of the wheel and are rotated by electric motors. Each excursion lasts the length of time it takes to complete one revolution. The observation wheel has a diameter of 120. Okay, so the first two paragraphs haven't a huge amount of information that will be useful. The 3.5 million could come into a question later on, or 32 passengers could come into a question, but this definitely will. So we have a diameter of 120 meters. And then it says the center of each passenger capsule is 4 meters. So the passenger capsule is 4 meters from the external circumference of the wheel, and the center of a passenger capsule is 6 meters above the ground when the passengers enter the capsule. So the wheel does not usually stop to allow passengers on, as the rate of movement is slow enough to allow visitors to walk on and off the moving capsule. The wheel can complete 2.5 revolutions per hour if it does not stop. So question asks, what is the maximum height? So we've actually two parts to this question. First one is, what is the maximum height that the center of the passenger capsule reaches above ground level? And two, how long does it take for the capsule to reach this height if the wheel is not stopped? So really that's our half a rotation. So let's look at a little diagram here. So we have some information. They told us that the diameter here is 120 meters. As well, I think I've gone a bit too big of my diameter. So my diameter roughly about there. We then also have the passenger capsule at each side. So that's 4 meters they told us. And then as well as that 4 meters, we know that this is 6 meters above the ground. So not perfect because my diagram is very small there, but that's all the information that we have. So how high, or what is the maximum height? So let's call this H max. That's going to be 4 plus my 120 plus 4 plus 6, and that gives me 134 meters. Now, the second part of that question says, how long does it take for the capsule to reach the height if the wheel is not stopped? So we know 2.5 revolutions per hour. So if we flip that, we'll be able to figure out how long one revolution is. So one revolution, the time to do that is going to be 1 hour divided by 2.5. Now, that's going to give us a decimal. That gives us 0.4 hours. And I'm not a huge fan of working with decimals when we're talking about hours. So another way we could do that, the revolution, is instead of 1 hour, let's go 60 minutes. And that will give us our answer in minutes, which is slightly nicer to work with. So this gives us 24 minutes. So one full rotation is at 24 minutes. And they asked us the height, how long does it take to get to the max height? So that's the top, which would be half a revolution. So then half a revolution is going to take 24 divided by 2, which is 12 minutes. Or if you really wanted to keep working in hours, you could divide your 0.4 and get 0.2 hours. Just decimals and hours and minutes, really easy to get things wrong there. So I would suggest to stay in minutes. So part B says, find the angle of rotation of a passenger capsule from the point of entry to the capsule after 5 minutes. So this is actually quite a straightforward question because we know, again, one revolution takes 24 minutes. So what fraction of the revolution is 5 minutes? So if we put 5 over 24, that can't be simplified. So that's how much of a revolution we've done. And if we want to think of terms of an angle, what is 5/24 of a revolution, which in this case will be 360 degrees. Now, if you want to work in radians, you can, but there was nothing in the question to kind of guide us towards radians. So I would suggest sticking to degrees, but it's completely up to you. And when we do that, we get 75 degrees, or if you really, really wanted to, 5 pi over 12 radians. So a really nice, straightforward question, but just the way it was asked, it could be tricky to figure out exactly what are they looking for. So the angle of rotation is really, what fraction of that circle, and that's what we're talking about. What we can do in kind of this case is go one step further and kind of say, well, look, there's one revolution every 24 minutes. So you could figure out, well, how long or how many degrees do we have per minute? So if I divide 360 by 24, I get 15 degrees per minute. So that's how much it moves. And that might be useful later on in the question. And you could have used this and then multiplied your answer by 5 to get your 75. But going straight to fractions is fine for this question. So part C then says, write down in terms of t the angle of rotation of a passenger capsule at any time where t is the time in minutes and after a person enters the capsule if the wheel is not stopped. So this is where I suppose it's useful, if we hadn't done it the last time, to say that again, we're moving 15 degrees per minute. T is time in minutes. So then if they're on for 2 minutes, it'd be 15 by 2. If they were on for 3 minutes, it'd be 15 by 3. So then the angle, I'm going to just go and call it theta, will be 15 times t. Okay, so it's 15 times t because it's 15 degrees t. Now, again, if you want to talk radians, our 15 degrees, it actually is pi over 12 t if you want to talk in radians. So that's in degrees, so theta is equal to pi over 12 t radians. But I wouldn't approach this question in radians because they didn't ask, so there's no need. So then it says, hence by drawing a sketch or otherwise, find an expression for the height in meters of the center of the capsule above the ground level in terms of t. So we want a formula that will get us t, or will get us the height no matter what t is. This is actually trying to put the function together. So this is what we have. We have our Ferris wheel. Let's say that's the external piece, or if you want to think the passenger. So we're talking about the mid of the passenger cart. So that's what that circle is. So it includes the circle plus the passenger cart. And then we have our midline. So this is 70. So let's think how we got that. So we know that the passenger car is 6 meters above the ground. The car itself is 4 meters to the external circumference. And then it's 60 meters. That's half the diameter. So remember, the diameter was 120. So that means the radius is equal to 60. So my 70 is made up of 6 off the ground, 4 plus my 60. And that's where we get that. So this gives me 64 from the center of the wheel. 60 is the radius to the outside, or the external circumference, plus the 4 that will bring us to the center of the passenger car. So this is 64. And that 64 is important because that's actually going to be my amplitude. That's what it changes, because that passenger car is going to be stuck to it the whole way around. So it's going to go 64 down and 64 up. So this amplitude is 64 meters. And that 70 was the midline. So you might kind of cop onto what we're doing here. We're kind of working with this as a trigonometric function. We're getting our midline, our amplitude. We want to figure out if it's positive or negative. We want to figure out if it's sine or cos, and we want to figure out our c. So before I go any further, let's figure out if it's sine or cosine. So where does this start? So we're starting here. This is where a person enters the London Eye. So because we're starting at the bottom, or really we're not starting at the midline, this is a cosine graph. So it's a cos graph. So let's highlight the piece of information I have at the moment. I have my amplitude. I know it's a cos graph. I know it's a midline. It's also going to be negative. And the reason I know it's negative is it starts, the first movement is below the midline. So if you look, here's my first movement going there. So it's underneath the midline. So it starts at the bottom. That's how we know that it's negative. So we are going to use our usual function. I'm going to call it h rather than f of x. So h, I'm going to h of t, because it is in terms of t, is going to be a plus b cos ct. What do we know so far? A is always our midline, so that's 70. It'll be plus or minus. So the b could be negative. In this case, it is negative because it's a negative graph. B is the amplitude, so that's 64, cos of. Now, C, there's a few different ways to think about C. So C is equal to 360, because we're dealing in degrees, divided by the period. So the period is, if you think about it, the time it'll take for one rotation. But an easier way is to think of C as the number of rotations, the number of times we rotate when we think we would normally rotate. So it normally rotates 360, and actually now in this question it's rotating every 24 minutes. So let's work with the period. It's going to be pretty much the same calculation. So 360 degrees divided by the period. So how long it takes for one rotation, which in this case is 24. So when I do that, I get 15. So I get 15t. Now what's interesting about that 15t is actually the C part 1, we'd already done that. So actually when it worked out that angle at any time, we were really working out that CT. Now, if you want to again go in radians, instead of 15t, it's going to be pi over 12 t radians. But I would stick with degrees. Now, this is like the older question. So a few years ago, we would have seen a lot more of these. We're seeing less and less now. It says the wheel does not normally stop to allow passengers to embark and disembark, and therefore the speed of the wheel is constant, suggest a reason why this is desirable. So I suppose this is nothing really maths related, but it was trying to connect it to the real world. But actually, it can be quite difficult to answer these types of questions. So I wouldn't get too bogged down in these types of questions. But here are some examples of answers you could give. So it's a smoother trip. So if you can imagine, it's not stopping and starting. As it stops and starts, that will give a lot of swinging to the capsules. So it's much, much smoother. And it's easier on the motors because the motors will be braking, restarting, braking. So constant motion at the same speed is much, much easier to manage than stopping and starting. So you probably have you may have other examples, and that's absolutely fine, but they're two kind of the main reasons. So the next part asks us to complete the table below to show the height of the center of a passenger capsule above the ground at 2-minute intervals for the time period shown. So I'm using my function, which is the height is equal to 70 minus 64 cos of 15t. And when I plug in t equals 0, I get 6. When I plug in t equals 2, I get 14.6. When I plug in t equals 4, I get 38, and so on. So I'll show one as an example. So I'll take h of 4. So instead of t, I'm putting in 4. So 70 minus 64 cos of 15 by 4. Make sure in your calculator there's external brackets there as well. If not, you may get a funny answer. And rounding that, we should get 38. Make sure you're in degree mode, because remember, this is a degree function. So this, you may have got this wrong if you got the function wrong. And what we're seeing again in more recent questions is that they'd ask you to show that the function is this. So then even if you got the function wrong, you still have the right function that you can work on this part. So then it says, using your results from part I above, draw the graph to show the height of the center of the passenger capsule above the ground for 2 complete revolutions. So here is roughly what we should get. It goes up to our maximum height here of 134 meters. We worked that out at the very first question. It starts down here at 6 meters. That's our absolute lowest. It rotates 24, so there is my 24 minutes. It wanted 2 rotations, so there is my 48 minutes for my second rotation. We're going to use the graph in the next part. It doesn't have to be perfect, but you do want to be able to use it. It does say graph it as opposed to a sketch, so we do want some level of accuracy. Part E then says the most spectacular views of the city can be seen while the height of the centre of the capsule exceeds 90 metres above the ground. Use your graph or otherwise to calculate the length of time during the excursion for which these views are possible. Give your answer correct to the nearest minute. So we can work it, and I will show you how to work it more accurately, but here is my graph, and I've highlighted in orange the section that's above 90 meters. So all I've done is I put a horizontal line at 90 and I've highlighted above. So that is between roughly 7 minutes and 17 minutes. So the question asks the length of time. So the length of time is going to be 17, take away the 7, which is going to give us 10 minutes. Now, if you didn't want to use your graph, and I suppose you can only be so accurate with your graph, but if you didn't want to use your graph, let's see another way we could work it. So we're going to treat this like the solving question we would usually see in section A. So it's asking us 90 meters above the ground. So I'm going to take my function, and the function is 70 minus 64 cos of 15t. Remember, we're in degrees, and we're trying to find it greater than 0. Greater than 90. Now, this can be a little bit tricky to do. If you want, ignore the inequality for a minute, and let's just work with the equation, so where it's equal to 90, and we're looking for times outside of that. So we're going to get the 2 points where it's equal 90. One of the points we want a little bit after it, one of them we want a little bit before that. So working this through, I get minus 64 cos of 15t. I take that 70 from both sides, that gives me 20, and then dividing both sides by the negative 64, and that simplifies down to minus 0.3125. What we would usually do at this point is we change it maybe to something like an x to simplify this question, and then we look at our unit circle. So this is cos is positive, all of them are positive, sine is positive, and tan is positive. So we're looking where cos is negative, so we're looking in quadrant 2 and in quadrant 3. So we're talking about this angle here, and then one down there as well. Both of these can be represented with a smaller acute angle, which is our reference angle. So we could say, well, the cos of that reference angle is equal to the positive version, so 0.3125. Make sure you are in degree mode here. I know it looks a bit funny, but we are in degrees. Cos inverse 0.3125 to work out A. This is the difference with our section A versus section B questions. When we were solving in section A, we would never usually have this quite like this decimal. We would usually be able to use page 13 to look this up, to look up that angle. So my angle when I do that is 71.79 degrees. We want this correct to the nearest minute, which will be the whole number. So 2 decimal places is sufficient. So now that I have A, let's look at quadrant 2 first. So quadrant 2. So in quadrant 2, we are looking at the angle that adds to A to make 180 degrees. So X will be 180 degrees, take away A. So X in this case is 180 degrees, take away 71.79 degrees. So X is equal to 180 8.21 degrees. We only want two answers. We don't want any rotation, so I can go straight here. Instead of x, I can say, well, 15t is equal to 108.21 degrees. So that gives me here the answer t, dividing both sides by 15. And I end up with 7.214. This is time, so we're talking in minutes. This wanted to correct the nearest minute. Now, this is the first angle, so we want it between these two. If you can picture, let me go back to my diagram for a second. We're picturing between this line and this line. So we want it a little bit more than here, but a little bit less than that. So we're going to round up, or if you want to use your inequalities again, we're talking where t is greater than 7 minutes. So that's going to take into account the numbers bigger than 7. We're now going to work with the quadrant 3, and we're going to do something similar. So let's do quadrant 3 up here. So quadrant 3, and we have x is equal to, in quadrant 3, 180 degrees plus your angle A, which means 180 degrees plus 71.79 degrees. Apologies, I forgot my 9 down there. And then when I add those together, I get 251.79 degrees, which I can go straight to, well, that's 15t, 251.79 degrees, divide both sides by 15, and I get 16.786. And again, let's round it and use our inequality. So the second value where t is less than, not 16, but we have to round up to get less than. So it's going to be less than 17. So these lines roughly equal 7 and 17. And we're going between those two answers. So if you want to combine them, so we want, we want the length of time. So we do want to combine them. So the length is going to be between, so greater than 7 but less than 17. So the length correct to the nearest minute is 10 minutes. Now, you could ignore that inequality completely there at the end. You can come along, take away your 16.786 and your 7.214. You roughly get 9.6-ish, which would round to your 10 minutes. The graph is a much easier option in this question. It's much quicker. This is worth 10 marks. You have about 5 minutes to do it. It's a lot of work. Now, hopefully this is an area that you can do quite quickly, but I would definitely look at the option of using your graph in this case instead. So the final part to this question is to find the distance in a straight line from the point of entry to a passenger capsule at the start of an excursion to the center of a capsule 90 meters above the ground. Give your answer correct to 1 decimal place. The important thing to note here is there is 2 points where the passenger capsule hits 90, and it doesn't matter because the circle is symmetrical. It doesn't matter which one you choose to work with, you'll get the same answer, and that's why they didn't distinguish whether it was on the way up or the way down. So let's look at a diagram. So here is our Ferris wheel again. I've put in my midpoint, I've put in the ground. So we're talking about working from a bottom point here. So I've put in my 90 meters. I'm working with the right. Like I said, you can work with the left. There's no problem. So that 90 meters, the midline is 70. So we're talking about 20 meters above the midline. So there's my starting point, my point of entry. And this is my straight line. And they were very, very clear about that. They did say in a straight line up to this capsule that's here. That's 90 meters vertically above the ground. So we're trying to find that distance there. So just that length that I have marked in blue. Now, how are we going to do this? And the answer is we're going to be working with triangles. So we need a few more lines. So the first line I'm going to put in is a horizontal line here, which allows me to have a right angle triangle. Now I can use this triangle, and it's very, very helpful because I know the height. But I don't know much more than that. So I'm going to need to work with another piece. So I'm going to try get this vertical length, And to do that, I'm going to work with a second triangle, which is up here. Now, this triangle is special because, again, with being right angled, this line here is also a radius. So this is 64. So I have a right angle triangle with 64 there. What I'm looking for, and I'll use my highlighter to show it, is this length here because it equals this length here. I know the height of my bigger triangle. So I know that this is 90 meters, but the actual triangle itself, if I go from here to there, we're taking away the ground at 6 meters. So that's 84 meters. So let's work with a smaller triangle first. So I have my right angle here. I know that this is 20 meters because that's 20 meters above the midline. I know this is 64. So using Pythagoras, I can work out that missing side. So I'm going to call this y. So Pythagoras is c squared equals a squared plus b squared. So c squared equals a squared plus b squared. Let's fill that in. 64 squared is equal to y squared plus 20 squared. So y is equal to the square root of 64 squared minus 20 squared. You can do this whichever way you want. If you want to multiply them all out, that's absolutely fine. And that is the square root of 3696. And that can be simplified, and if you put that into the calculator, it will simplify that third. Now, I would probably keep the bigger one because we're going to work with a second triangle, so we're going to probably use Pythagoras again, which means we're end up going to square it, and squaring the square root just simply cancels out. So now I know y, and that is highlighted so we can see that's the yellow piece I've highlighted above. That is y. So I'm going to go to my bigger triangle now, and I'm going to work with that. Now, what I know about this one is that my height here is 84. I just worked this out. Like I said, I'm going to use this as 3696, and we're trying to find this length here, which I'm going to call x, and that's the straight line. And that will give us the distance in a straight line from the point of entry to the passenger capsule at 90 meters above the ground. This x is what the question is looking for. So just so you can see which triangle we're talking about, because I haven't done a great, doesn't really look like it, but there is that x that I'm looking for. So I'm going to use Pythagoras again. So there's CAB. C squared equals a squared plus b squared. I get x squared equals, so this is what I meant about that square root. So this just leaves me with 3696. I have 84 squared. And when I work through that, I get x is equal to the square root. When I put that in, I get 10,752. I need my answer correct to one decimal place, it said, so that gives me 103.7 meters. So that is my answer. Now, I suppose take a look at this and notice all we've done is 2 rounds of Pythagoras, something you probably learned back in second year. The maths is not the challenge. The challenge is trying to understand what they're asking. The best way to work with any of these questions, especially these section B real life questions, is to try and draw a diagram. Now that can be really challenging, and if you're there going, I never would have seen that diagram, I never would have been able to picture it, the answer is practice. You need more and more practice with trying to take what they're telling you and figuring out, well, what does that mean for me in a maths context?